So it's a great pleasure to introduce again Serena Dipierro, and today she's going to give the third lecture for us, third and last one. And so I hope you all enjoy. And so the microphone is yours, Serena.
Thank you, Juliana. Yeah, so I also hope you will enjoy it. Let's see. Yes, so yesterday we introduced this, we got acquainted with this object, which is the fractional Laplacian. And let me remind you the definition so that we can catch up with things. So the fractional Laplacian for a reasonably nice function given a fractional parameter s between 0 and 1 is defined as an integral differential operator. So it is an integral over Rn up to some multiplicative constant here of some kind of incremental quotient of order 2s. So I have my increment here in the numerator, and then I have a kernel which is like something polynomially decaying, so something like 1 over y and plus 2s. And of course, yesterday I remember someone mentioned also possible other possible operators. Yes, you can one can consider more general operators here, comparable with the kernel of the fractional Laplacian, but or with different type of decay. You can, but let me stick to the case of the fractional Laplacian, which is in a sense the prototype example and possibly the simplest one. So when s tends to 1, the fractional Laplacian, when multiplied by a suitable constant depending on s, so something like something that contains the term 1 minus s, would converge to the Laplacian. So we expect somehow some nice properties also for the fractional Laplacian, somehow that can be somehow inherited by the classical case, by the Laplacian. Okay, so we discussed a little bit of, so we proved that this function here, x plus to the power s, is s-harmonic in the half line, and we did the computation yesterday. Yes, and then we proved also this result, this density result that basically tells us that every nice function, a CK function, can be approximated by a function u epsilon, which is s-harmonic in V1, compactly supported, if you like, and it is close to my original function u in the CK norm, so some kind of strong norm. So this density result we will use it today to prove the fractional version of Courant theorem, at least for one of the two proofs that I'm going to give. And so this was the heuristic behind that theorem, that you can somehow, so you are forced to stay close to the red function in B1, but you can play with you have some room, you can play with the function outside B1. Okay, so we gave the proof. And okay, so we started now looking, so diving a bit into the fractional Malmheden theorem. So we started with the fractional mean value theorem, and we observed that the function u is s-harmonic in some ball, or if in the domain, if you want, if and only if for every ball contained in my domain, or in BR in this case, u at 0 can be written in this way. So the fractional mean value theorem is slightly different from the classical mean value theorem, essentially for two reasons. One is that we have to integrate not just on the boundary of the ball, but we have to integrate in the complement of the ball, because the fractional Laplacian, so a classical Dirichlet problem in the fractional setting would have, so would not have a boundary datum, so but rather an exterior datum. So you have to define the function everywhere. So usually one has to define the function everywhere outside B1. And so for this reason here, we have Rn minus Br and not just the boundary Br. And then we don't have just the function u, but we have some kernel. We have to weight it with the some kernel, which is sensible. I mean, it's reasonable to think about it, because we have to imagine that the interaction between points would decay as the points move far away. So there is some kind of decaying kernel here. So it is a reasonable thing to have. Okay, so then one can rewrite, if we like, to make the somehow the comparison with the classical case, we can rewrite the kernel in such a way that we write the fractional mean value theorem as an integral over the ball of v of y in some measure sense here. So we have d mu r, but d mu r is defined to be some weighted volume element here. So in particular, in the classical case, mu r, I mean, this is just the Lebesgue measure. Okay, so we are using the Lebesgue measure in the classical case. Here, we have a bit of a more complicated measure, but this is what we can expect in the non-local scenario. And if we write things like this, we have a fractional Courant theorem, so a Courant type theorem, that tells us that, okay, if I have a bounded and open set, and I assume that it contains the origin, and I call R the distance of the origin from the boundary of omega, so that the ball BR is contained in omega, and I suppose that a fractional mean value formula holds true also for omega in this sense. So we write d mu r here. The integral is now in the complement of omega, and I have to take an average. So I have to weight, I have to divide by the measure, this measure here of Rn minus omega. So if this is true for all s-harmonic function in omega, then omega has to be the ball. So I think yesterday someone asked, I think I said something about the fact that in the fractional situation, we have a measure that depends on the ball. And still, I mean, this doesn't make it easy to prove that omega is the ball. This is not obvious. The thing is, I'm not sure that if one put another measure here, then one can obtain a Courant type result, because this would be connected to what Poincaré called the Balayage Problem. And the Balayage Problem essentially is about somehow reconstructing an harmonic function or s-harmonic function in a ball given its boundary datum with some kind of measure here. So, I mean, if the Balayage problem has a positive answer, which it has, if the domain omega is sufficiently regular, you would have a Poisson kernel. So you would always have the possibility of writing u at some point as the integral over Rn set minus omega of u multiplied by some kind of measure here. So that would be, in my opinion, a different problem. That's why I said yesterday, I mean, it is reasonable that we put this type of measure, because this is the one somehow that, that if you like, converges to the classical mean value formula. And I would not expect that if you put a different measure here, then you would have a result of this type, because this would be somehow a different problem, like the Balayage problem, which is the one of finding the measure which essentially does this job. So that's why yesterday I said, okay, maybe it's not completely satisfactory result of this type, because you're somehow forcing the ball into the equation here, but still, I think that it's a reasonable choice at the end of the day. And we will see it's not straightforward to deduce that omega is a ball here. Okay, so I'll try to show you a couple of proof of this. And one will use the density result, that all functions are s-harmonic. And then the second one will use some potential analysis method. So we'll see. Okay, so the first proof of fractional Courant theorem goes like this. So I basically do the same procedure that I did in the classical case. So I suppose by contradiction that omega is not BR, so that there is something, that there are points in omega minus BR, and I choose a point P in omega minus BR. And then I can also say that since omega is open, I can find a ball. Now this P is in omega, so I can find a ball centered at P contained in omega. And now because BRP set minus BR is non-empty, and this set is contained in omega minus BR, I can see that mu R of omega minus BR is strictly positive. This is something that I will use later on. And then I play essentially the same game that Courant did in his proof. So I know that U is s-harmonic in B. I take a function U s-harmonic in omega with such that U at 0 is equal to 0. And so 0 is equal in particular to mu R times U0. And then I use the fractional mean value formula for U0. So this is going to be equal to the integral over Rn of U. And then again, because BR is contained in omega, I'll split the integral into two integrals. So one is in Rn minus BR, and the other is in omega minus BR. Now, BR, so my function is also s-harmonic in BR because BR is contained in omega. So I can use the fractional mean value formula for BR. So this is going to be equal to the measure times U0. And this is the same. And then U of 0 is equal to 0 again. So I don't have this term. So I end up here. And now if you remember, the idea of Courant was to choose a good harmonic function. Okay, so this is the game that we will try to play. And we will use that all functions are locally s-harmonic up to a small error. So for us, the error will be of order r squared. So in particular, I will take epsilon to be r squared divided by 4. I'll take a parabola, so I'll take a function f of x equal to x squared. And I'll take a reference domain B capital R, and capital R is the maximum of the norm of y living in the closure of omega. So B capital R contains omega now. Okay, so now I look at B capital R, and I have a function f, which is nice. So I can find a function now, f, that depends on epsilon, of course, which is r in this case, and capital R, such that this function is now s-harmonic in B capital R, and it is very close to f in BR. And very close means that the difference in the L infinity norm of the difference is below epsilon, which is r squared divided by 4. Okay, and then my function will be U star, will be minus this f little r capital R at x plus f little r capital R at x, sorry, at 0. And so now I want to check, if you remember, I want to see what happens to minus U star. Okay, so this function is good because it's s-harmonic in omega. Sorry. So this is the function that I want to plug into the equation at the end. So I want to check what happens to minus U star. So let's start with U star so that we don't mess up with the signs. So U star is minus f of x here, and then plus f of 0. So I will add and subtract f of x, which is here and here, and f of 0. And then I will put together f of x with this minus f of r, little r, capital R of x here, and same for 0, so this one and this one. And what remains is f of x minus f of x plus f of 0. Okay, so this is bounded by this difference plus the difference of the, so the absolute value of the difference here. And now f of x was x squared, so minus f of x is minus x squared, f of 0 is 0. And these two are both bounded by, if you remember, are bounded by epsilon, which is r squared divided by 4. So I've got r squared divided by 2 because I have two of them. And so this means that if I take x in B capital R set minus BR, so outside BR, then minus U star will be bigger or equal than x squared minus r squared over 2. But now x is outside BR, so this x squared is bigger than r squared, so all in all, this is bigger than r squared over 2. Nice. Now, omega is contained in PR, B capital R, and so I can use this bit into here. So I have that the integral of over omega minus B rho of minus U star is bigger than, well, this is bigger than a square over 2, and then I have the measure of omega minus BR, which we proved was strictly positive. So this object is strictly positive. And so this plays the game of the function H that we used in the classical current theory. And then again, because you started 0 is equal to 0, and this is harmonic, s-harmonic in B capital R, okay, we can plug it in our computation. So we started with 0. So 0 was equal to this object, but now we just proved that this is strictly bigger than 0, which gives a contradiction. So the contradiction comes from the fact that we assume that omega did not coincide with BR. And so we prove that omega is essentially BR. Okay, and then, so this proof is nice and similar to, kind of similar to the one provided by Curran, and uses a nice result in my opinion, which is the fact that all functions are s-harmonic. There is also a second proof that one can give that is, structurally different and is based on potential theory. And so the idea is that at the end of the day, because we are comparing the fractional mean value formula in omega and in a ball, at the end of the day, if omega is regular enough, and so you can define a Poisson kernel for omega, then you end up actually comparing the Poisson kernels of the ball and of omega. So if I assume for simplicity that the omega is a C11 boundary, I can use the fractional Poisson kernel. So, and I know the fractional Poisson kernel of the ball. It's written in this way. So it's some constant depending on n, the dimension n, and the fractional parameter s. And then here I have r squared minus x0 squared to the power s. And then I have for points that are outside. So here x is in Brx0 and y is in the complement. So this object is positive, this object is also positive. And then I have x minus y to the power n. And also, because the domain is regular enough, I can define a Poisson kernel for omega. So if U is s-harmonic, I can write U in terms of the Poisson kernel. So I can write U to be the integral over Rn minus omega of U against the Poisson kernel of omega. And so at the end of the day, if I look at this object here, so the integral over Rn minus omega of U multiplied by the Poisson kernel of the ball rescaled by the measure minus P of omega, well, this is essentially equal to, okay, so here I take 1 divided by the measure outside, and this is integral equal to the integral of U against the Poisson kernel in BR, and then this is equal to U of 0. This is what we just wrote here. Okay, and then okay, and then I use basically the assumption that I have on the fractional, that the fractional mean value formula is holds true in the for omega, and so this is equal to 0. And so if you see at the end of the day, since U is an arbitrary s-harmonic function, I ended up with an equality between the Poisson kernels. Okay, so the Poisson kernel of the ball and the Poisson kernel of omega. So the problem is reduced to checking whether these two kernels can be the same, or if I can get a contradiction. That's the idea. Okay, so this is an identity about fractional Poisson kernel, and we need to show that this identity between fractional Poisson kernels forces omega to be the ball. So again, we suppose by contradiction that this is not true, so that BR is strictly contained in omega. And then I can choose a point P star on the boundary of omega that is not on the boundary of BR. Okay, and then I take points outside, I will take points outside, outside omega, and they will tend that, okay, I will take some, let's say, a sequence of points from outside omega that converges to P star. And then if we do this, the right-hand side will tend to infinity. So this object here will tend to infinity because the Poisson kernel of omega should blow up at the boundary, but this one will not blow up because this is a finite quantity, because the point does not live on the boundary of BR. And so essentially this would give me a contradiction. So if omega is sufficiently smooth so that I can define a Poisson kernel, I'm basically done. But what if omega is not smooth? Well, we have to somehow do some kind of approximation, so smooth the domain out and smooth our equations out so that we can play essentially this game. So the technical details go as follows. I will take a ball. So I have a picture here, so maybe it's easier. So I have BR here, which is strictly contained in my domain omega, which is the green one, which is not smooth. And I will take, you see, I will take a ball, B star, that is contained in omega minus BR, such that, B star touches the boundary, so the boundary of B star touches the boundary of omega at some point B star. Okay, so this is what is written here. I will pick a point B star on this boundary, and then I will take a sequence of points Pj outside omega that converges to P star as j goes to plus infinity. So I have P star here. I can't define the Poisson kernel for this object, but I will try, because omega is not smooth enough, but I will try to somehow smooth omega out, and then I will choose a sequence of points Pj convergent to P star, so that for these points outside the suitable smoothing of this domain, I can play this game of the Poisson kernel. So this is the idea. So we will see it's a bit technical, but essentially the idea is that I'm trying to recover this argument of, identity, ending with an identity of Poisson kernel. But this is somehow hidden in the technical details. Okay, so I will call var P BR, the union between BR and B star. So var P is going to be the yellow ball here, BR, and union with B star, the red one here. And then we will see, I will basically construct a harmonic function in B1, which essentially corresponds to the Poisson kernel at Pj, Poisson kernel with the pole at Pj. Pj, remember, are points coming from outside omega and going towards P star. And so on the one end, I will have that this function will have to reproduce the Poisson kernel at Pj, so with pole at Pj. But on the other end, we will see that the corresponding average will converge to a finite value, and so we will get a contradiction. So this is the game that I want to play. So the details of the technical argument, which is, yes, a bit technical, go as follows. So we take a nice function, so infinity compact is supported in B1, and which takes value in 0, 1, even, and such that its integral is equal to 1. And then I'll take a rescaling of this function. So k will be a natural number. So phi kp of x is going to be k to the power n, phi of k multiplied by the x minus p. So essentially, this modifier here will converge to the Dirac delta centered at the point P as k goes to plus infinity. So I'm mimicking, in this problem that I'm going to solve, I'm mimicking the idea that I want to have the Poisson kernel at the end, because if I had a Dirac delta here, the solution would be a Poisson kernel. But I'm trying to play this game coming from outside so that I don't have regularity issues. So UKP will be the solution of fractional Laplacian of UKP equal to 0 in var P. Remember, var P was the union of the two balls. And U equal to this phi, this rescaling of phi outside. Okay, so UKP morally is our Poisson kernel centered at P. So it will be centered at Pj if we write UKPJ. Okay. So also given J, I will suppose that K is large enough such that, so remember, Pj is outside omega. I will take J large enough such that, K large enough such that the ball centered at Pj of radius 1 over K is outside omega, still outside omega. Okay, now I want to smooth my set. I want to smooth out my set. So I will take another parameter delta, and I will take, I will consider omega delta to be a smooth and bounded open set that contains omega, and such that all points of omega delta have distance less than delta from omega. So it's a fattening of omega that would smooth this out. And again, I take delta sufficiently small such that the ball center the PJ of radius 1 over k is still outside omega delta. Okay, and then I do the same that I've done before. So now I take u, k, pj delta to be the fractional harmonic function. So it is, again, s-harmonic in var p, but that now coincides with the phi, with the phi k pj outside omega delta. And we claim that now this construction, okay, what I'm doing, I am enlarging a bit omega delta. So essentially by maximum principle, we will see that this UKPJ delta is above the UKPJ. So the function that is harmonic in var p coinciding outside to the function phi. So why is this true? Well, by maximum principle, UKPJ delta is positive because the outside datum is positive, so and the maximum principle is satisfied. And also, I have that UKPJ, so outside Rn minus var p, and outside B1 KPJ. So if I am outside the ball, B1 KPJ. So UKPJ is equal to phi KPJ because I am outside Rn minus var p. This was the problem that I was solving. And because I am outside B1 KPJ, phi KPJ is 0. So this was compactly supported in B1 KPJ. Okay, so UKPJ delta is positive. And 0 is UKPJ. So the claim is true, at least in this set here. So Rn minus var p intersected Rn minus the ball, which contains Rn minus var p intersected omega delta. Remember that P1 KPJ was outside omega delta. So I have this inclusion. But if I look at Rn minus omega delta, well, these two functions are the same because outside they have both the same exterior datum. And so at the end of the day, this inequality holds true in Rn minus var p because it holds true in Rn minus var p intersected omega delta, but it holds true also outside omega delta. So in Rn minus var p is true. Okay, but they both satisfy an equation, so they are both s-harmonic in var p, and they are ordered outside var p, and so I can do again the maximum principle and conclude that they are ordered. So UKPJ delta is bigger than UKPJ. Okay, a second ingredient that I need is this convergence. So I want to prove that if I take the limiting delta now, or the integral over Rn minus omega of UKPJ delta, well, I end up with the same integral with var phi. Okay, so this is intuitive in a sense, because I am kind of converging to the UKPJ in a sense. So to this end, we observe that the image of phi KPJ is 0k. So remember, the original var phi was in 0,1, and here I'm just rescaling. So this is in 0k. And so by maximum principle, because this is the bounded, the exterior datum related to my function, by maximum principle, also this one is in 0k. So I can essentially do dominated convergence and pass to the limit. This is the idea. So this object here, which is this one in blue here on the left, can be split into the integral outside omega delta and then the integral in omega delta minus omega. Now, outside omega delta, UKPJ delta coincides with KPJ. So this is good. And here I leave omega delta minus omega. And now if I send delta to 0, again, as I said, I can essentially apply the dominated convergence and obtain exactly this limit. So this object will go to 0 because omega delta is convergent to omega, and this object will go to the integral over Rn minus omega. Okay, so now I use these things together. So now UKPJ at 0 is below UKPJ delta at 0. So I take the limit in delta here. And then UKPJ delta, here I can use the mean value theorem. So this is equal to the integral to 1 over the measure, the integral in the complement of omega. And then we just prove that the limit in delta of this object converges to the limit of, the integral of phi kpj. Okay, so all in all, I have that UKPJ at 0 is below this object here, so this average here. Okay, and now I'm very close because, so as I said, so UKPJ at 0 converges in K because the var phi in K, as K goes to plus infinity, converges to the Dirac delta. This object here is converging to the Poisson kernel of the set var P centered at Pj. This one here, we just proved that is below this average. And now I can send K to infinity. And if I send K to infinity, again, this phi, the modifier here, will converge to the Dirac delta. So what I have here is nothing but basically all this object, so this integral in d mu r y, evaluated at Pj. Okay, and now you see where I'm going. So I got from, so on one side, I have a Poisson kernel of Pj. And the reason why I had to do all this construction is because I wanted to apply, so var P is a regular domain, so I could have defined the Poisson kernel in principle, but because I wanted to apply at some point the fractional mean value theorem, I wanted a function, so I didn't want a problem with the Dirac delta. I wanted a function defined everywhere. So I had somehow to play this game of smoothing things, use the modifier, and then pass to the limit. So then I could use essentially the fractional mean value theorem to my nice and smooth function. And then I could pass to this function, I mean, whatever I get, whatever identities I get to the limit. So on one side, I get the Poisson kernel, fine. Because I didn't want to use the fractional mean value theorem to the Poisson kernel, because that's a Dirac delta outside. So I didn't like, I wanted to use it on a function. I said that's true for functions. Okay, so here I will have something that we will see will blow up, and on the other end, we will have something that is actually convergent. So we use now the geometry of the fractional Poisson kernel, because we know that the Poisson kernel essentially behaves like this. So it is bigger or equal than something, and the important part, I think, is the distance of Pj from the boundary of Rp here, because this object will explode if I send j to plus infinity, because Pj would converge to P star, and P star is on the boundary of Rp. So this distance will get to 0. So this object in j, as j goes to plus infinity, will blow up. This object here. Yeah, so this is what's written here. Because Pj is convergent to P star, this object will blow up. And so you see, I have something that goes to plus infinity here, bounded by the limit of this object here. So the limit of this object here. But this limit, so Pj is going to P star. So this is equal to the same equality with P star in place of Pj. But now remember, P star is not sitting on the boundary of Vr. So there is nothing here that blows up. So this quantity is finite. And so I got a contradiction. So as you see, it's a bit technical, and actually I have omitted a lot of other technical details here and there. But the idea is that, okay, I reduce my problem to comparing fractional Poisson kernels, and then I try to get a contradiction from there. And then because I want to deal with nice and smooth domains and nice and smooth functions, nice functions to use whatever I have to use, then I have to do a bit of technicalities. But the idea is that I'm comparing Poisson kernels. Okay, so we have two proofs of the Courant theorem, and so I think we can consider ourselves pretty satisfied with this theorem. And now the next step at this point is the fractional Malmheden theorem. So I want to see whether I can obtain, I can cook up a geometric argument, a geometric construction to define s-harmonic function in a ball given a boundary datum. Okay, so I want a geometric argument to construct s-harmonic functions in a given ball, given some boundary datum. And I'm writing boundary in this way because it is, as you see, it is not really a boundary datum, it's an exterior datum. So again, this is the way you would set a Dirichlet problem in the fractional setting, because this fractional Laplacian sees the function everywhere, so you have to tell him what the function is everywhere. So everywhere outside V1 in this particular case. So our boundary datum is going to be an exterior boundary datum. So can we make a geometric argument to construct a function, an s-harmonic function of this type? Yes, at the end of the day we can. And there are a couple of structural modifications. As you could see already, the fractional mean curvature formula was different from the classical case, so we had to add a weight in the integral. Here is going to be the same in a sense. So weight somewhere. Sorry?
Serena, the voice stopped a little bit.
Okay.
Your voice.
Where have you lost me?
Yeah, I think at the beginning of this slide.
At the beginning of this slide. Okay, so so this is fine.
Yeah.
So this slide is fine. Okay. So let's try again. Sorry, I think yesterday it was at the same time that the connection somehow dropped a bit. I don't know why. Probably everybody connects at this time. I don't know. Yes, so we want to cook up a fractional counterpart of Malmheden theorem. So we need to employ some modification. So we've already seen with the fractional mean value formula that the fractional counterpart is slightly different because we had to add some weight. So we understood that the situations are those two situations are a bit different, because in the non-local setting, the points interaction has somehow to be weighted in order that points close by count a bit more than points far away. So we understood it's reasonable that we have to add some weight. So the same thing happens here. So we expect something like that here. So here the modification that we will employ are the following. The classical spherical averages have to be replaced by suitable weighted spherical averages. So we will have some weights. And then the geometric transformations involved will be scaled in dependence of the radius of each of these spheres. So as you can imagine, we will be integrating outside a ball. And we will see that if one writes the complement of a ball in spherical coordinates, well, each of these ball have to be somehow scaled in some way. They have to have some quantities that are scaled in some way. Okay, so let me now write down the setting that we work in. So we define, so if I have a function f, I define f of rho to be the suitable scaling of the function. So f of rho of x is f of rho x, and rho for us will be bigger than 1 in the game that we are going to play. And then I will call mat-kalel f(ab) the affine function such that this function evaluated at a, so at the first endpoint, is equal to f of a, and the same function evaluated at the second endpoint is f of b. Okay, so this is like we did in the classical case. We are trying to take the affine function passing through a point in the ball connecting basically two endpoints. But this is not enough, and here the notation gets even uglier. So I have to rescale this object, and we will see why, because here we are not integrating just on the boundary of the ball, we'll be integrating in the complement of the ball. So if I use polar coordinates, I will be integrating over the boundary of these balls B rho. So I will need to rescale a bit if I want to write something of this type on these balls. So rho will be bigger than 1 for this reason. Okay, and so I will define L, F, E rho of X to be the affine function, but now that sees basically, that interpolates the values of f of rho instead of the values of f, with endpoints x minus and x plus. And all this has to be evaluated at x over rho. Okay, so, okay, let me recall our picture. So here I have, so remember in the classical case, I had P and I had Q minus and Q plus. So this is what I'm taking here, but all this has to be evaluated at x over rho. Okay, so the idea is that if I have a point that is outside the ball, I want to rescale it to make it inside the ball. So I will divide it by rho. Rho will be bigger than 1, so that then I can play this game. So that's why you have a rescaling here, because you have to take x outside and bring it in the ball and then play this game. Okay, and then this is the kernel, that will weight our integral. So it's this mat-Kali of x rho, which is some explicit constant multiplied by some objects here. So, and here again, this is a kernel for the ball B rho. Rho again is bigger than 1. So rho square minus 1 is positive here. X will live in B1 at the end of the day. So this is positive, and also this is positive. So more or less, this is the Poisson kernel when you pass to polar coordinates and you look at it just on the boundary of some ball B rho. This is what I'm doing. Because essentially the idea, if you remember when we were talking about the classical Malmheden theorem, the idea of Malmheden was that, okay, he knew that the function could be written in terms of the Poisson kernel. So going back with the computation that we did, from the Poisson kernel, one can arrive to the at the geometric expression that we have. So here we'll be playing the same game. I mean, that's the way we proved it, because we know that a function can be written on the ball in terms of Poisson kernel. So what can you do? Okay, you start from the Poisson kernel expression and you go backwards. And if you do that, you use polar coordinates and you will see that you will end up with the Poisson kernel written on boundaries of balls, if you write things in polar coordinates. So this is the idea. So this is reminiscent of the Poisson kernel. And so essentially this is what we have. So U at P, so if I define U at P, sorry, so I think this is U of X. This is U of X, sorry, it's not P. Yes, so U of X is the integral from 1 to plus infinity of the integral over the boundary of B1. So here you see I have an integral outside B1 in the complement of B1, but written in once you pass to polar coordinates. And then I have this interpolation object, the geometric object, or this interpolation of a fine interpolation of points. And here I have my weight kernel. Then if I do like this, U is the solution of the fractional Dirichlet problem in the ball. So this U solves fractional Laplacian equal to 0 in B1, U equal to F outside B1. And F is hidden here, because this object here sees a fine function interpolating the two endpoints. Okay, so in particular, when, it's when X is equal to 0, or P if you write P here. If you remember, we had that essentially R plus of minus were equal to plus and minus 1, and Q plus of minus were equal to plus and minus E. And so this object here, So of course we expect that when x is equal to 0, so I'm looking at the center of the ball, I have to have back my fractional mean value formula, which is what we are going to check now. So in this situation, this interpolating function here, which was by definition this object, now q minus and q plus are just minus e and plus e. And this is equal to f evaluated, so f rho evaluated at e, so f of rho e, and then f rho evaluated at minus e, so f of minus rho e, and in the denominator you get the distance between the 2 points, so the distance between the norm of e minus minus e, which is 2. And also, if you write the kernel at 0, well, you have some kind of simpler expression here. You can get some simplification once you take x equal to 0 in the kernel. And so if you plug this, if you use these considerations into the fractional Malmheden formula, you end up with u of 0 equal to these two objects evaluated at 0. So you substitute what you got. The interpolating function here is this one here. And then,
sorry, Serena, can you go back to the previous slide very quickly?
Sure. Yes. Okay, so the first one here is just the definition. Here yeah, I'm using this here, yeah. And then I'm writing. So if you remember, the interpolation was the function evaluated at one of the two divided by the distance between these two, plus the function evaluated at the second one. And now the function is f rho, so it's f of rho e and f of minus rho.
So okay. So divided by the distance between the 2 points.
Yeah, this is basically the norm of e minus minus e.
Yeah. Okay, I didn't remember the definition.
Precisely. Yeah, probably I should have written it here, but yeah, that's what I'm doing. If you remember, like, I wrote it explicitly, I think in the first lecture.
No, it's fine.
Yeah, because this is interpolating. I think this is interpolating. I think this is interpolating e and minus e. So it's the function that interpolates f, so the value of the function at e with the value of the function at minus e. So if you write it down here, this is what you have.
Okay, it's fine.
Yeah. Okay. And then this is really just taking x equal to 0 in the kernel that's written here. So you don't have this object here because this is 1 minus 0. And here you will have rho squared. So you will have a cancellation.
Yeah, it's fine. Thank you.
Okay.
Thank you a lot.
Okay, so I plug this into the fractional Malmheden theorem. So the kernel is here and the interpolating function is here. And then I call rho e omega and I do this change of variables. So I end up with some rho n here coming from the change of variable, and then I have omega here and minus omega. And then I do another change of variables. So I think I call y to be rho times omega divided by the norm of omega. And so basically I do I go from polar coordinates to the integral over Rn minus b1. So now my new variable is y. And then you see the last thing is just splitting the two integrals and passing here from minus y to y. And so this is going to be essentially the same thing. So I have divided by 2, which will give me just 1 now because I have 2 of them. And so this is going to be a constant multiplied by an integral outside B1 of the function divided by the right kernel, which is in the fractional mean value theorem. So this formula is reasonably good, at least good enough that when you compute it at the center of the ball, you recover the fractional mean value theorem. So this is what a first sanity check that the theorem is reasonable. And also one can check, we will not give the proof here, but one can really check that when S goes to 1, the fractional Malmheden theorem recovers the classical one. So if you send S to 0 here, you recover the fractional Malmheden theorem. So in a sense, the integral from 1 to plus infinity weighted by this kernel would somehow average out, and I will just end up with an integral over the boundary of the interpolating function. So this recovers the classical Malmheden theorem, which is
sorry, Serena, can you repeat very quickly the end of the proof?
Here?
Here, yeah. When you have the integral sorry, on the boundary of Pirot, this quantity.
This one here?
Yeah, it's just.
Yeah, I mean, if you do from here to here, it's just into polar coordinates.
Yeah,
so it's like a thing.
Yeah.
Okay, it's just polar coordinates. If you do the computation, it's
okay, no, of course. And the last step is.
And the last step is just splitting the two integrals. So the one with the y and the one with minus y. Yeah. And then in the second one, you switch minus y into y. So you call z minus y. So this would be for z, and here this is even, so this is fine. So the two are exactly the same.
Yeah, thank you.
Okay, and this is now the fractional mean value form. Okay, and then and then we said when S goes to 1, the fractional Malmheden theorem recovers the classical one. So we have at least a couple of good reasons to think that that was a reasonable formula, because it recovers the fractional mean value formula when I compute it at the center of the ball, and when S goes to 1, it recovers the classical Malmheden theorem. So it's a reasonable formula. Okay, so I'm not giving you the full proof of the fractional Malmheden theorem, but of course, once we guess the right formula from some geometric considerations, the proof relies on a series of identities due to the geometry of the projection. So what one does, as I was mentioning before, one starts with the representation of the s-harmonic function in V1 using the fractional Poisson kernel. And this, of course, produces an integral in the complement of V1 that I can write in polar coordinates. If I do this, I can play a bit with the scaling and recognize the kernel E as a weight for the integral. And then I name whatever remains. So once I take E out, I recognize E, I isolate it. Whatever remains, I can call it G. And then I can apply the spherical change of variable that we discussed when proving the classical Malmheden theorem. And then once I do this, then I go back to my function, I rearrange a bit the term, I detect cancellations coming from the geometry of the problem, and I'm essentially done. So it's very similar to what is done in the classical case, but if you remember, the difficult bit was to prove the change of variable formula. The rest was really somehow clever manipulations of the integral and the application to a suitable function of the spherical change of variable that we did. So here is similar, but the idea is that you have to prove that that expression is equivalent to the one with the fractional Poisson kernel. That's the game that you want to play. Okay, and then one can also prove a fractional Schwarz theorem. So once you have the fractional Malmheden theorem, one can prove the fractional Schwarz theorem. So this is also done in collaboration with Giovanni Giacomin and Enrico Valdivoci in a paper that is, I think is on archive, or I'm pretty sure it's online somewhere. But if you want to give a look and you don't find it, you can certainly send me an email and I will give you the reference. So in dimension 2, the fractional Schwarz theorem is in dimension 2. And here, of course, we don't have the interpolation the interpolating function here. If you remember, in the classical Schwarz theorem, we had an integral over the boundary of B1 of f evaluated at the second endpoint, like the one with the minus sign. So here is the same, just that again we have the weight, the same weight, and we are integrating outside the ball. So once you pass to polar coordinates, you end up with something of this type. And then if you write U in this way, then U is the solution of the Dirichlet problem in the ball. So it's s-harmonic in B1 and is equal to F. So this is R2 in this case, minus B1. And again, when S goes to 1, the fractional Schwarz theorem recovers the classical one. So if you send S to 0 here, you will see that basically this integral in the complement of the weight will average in such a way that when S goes to 0, we just end up with the integral of the boundary of B1. So a local case. And also here, if you remember, in the classical case, we were able to compute the temperature of like, I don't know, a metal plate, a disk, knowing the temperature at the boundary, just using this geometric consideration given by Schwarz theorem. And here you can do the same. So just that here, of course, you have to define a function everywhere. So if you fix an arc sigma on the circle boundary of B1, now I'm in R2, and then I call sigma star to be the cone generated by sigma. So sigma star is the set of points such that the direction, so x divided by the norm of x, belongs to sigma. So once I have an arc on B1, I have to take the cone generated by this arc. And then I can consider now the solution of the fractional Dirichlet problem in a ball with conical exterior datum. So here I don't have just the arc, I don't have just the characteristic function of the arc, I have the characteristic function of the cone. And again, the question is, do we have a geometric way to represent such a solution? And the answer is yes, because we can use also in this setting the Schwarz theorem, the fractional Schwarz theorem. So if I take x over rho, which is now a point in the ball, and I take sigma prime of x over rho, which is the projected arc of sigma on the boundary of B1 through the point. So I can give you a picture. So I have B1, and then I take a point, I don't know, I have an arc sigma. I'm very bad at drawing pictures, so this is going to be bad. So this one that I try to color in red is my arc sigma. And then I take a point x over rho, which is now inside the ball. And then, of course, I have to take the projection of the two endpoints of the arc sigma across x over rho. And whatever I have is going to be my sigma prime x over rho. So here is the picture. So I have the ball, the arc sigma, I have x over rho, and then of course I project sigma through x over rho, and this is the conjugated arc that I get here. And okay, this is the length, and then the fractional Schwarz theorem yields that, like in the classical case, u of x is equal to the integral 1 to plus infinity, and then I have an integral over the boundary of B rho of the characteristic function of this object, which is just the length of this object times the kernel. And that is, U is a superposition of scaled arc lengths weighted by the kernel A, because here rho, so rho is moving from 1 to plus infinity, so x over rho is moving here, So and every time that I change rho, I have to take the new conjugated arc, and U of x will be given by the superposition of these arcs. And then in particular, if I compute it at the center, so U of sigma is going to be actually the length of sigma, because if I take the conjugated arc of this with respect to the center, the length of the conjugated one, it will be the same as the length of sigma, because they will be symmetric with respect to the origin. So here we just get, every time is going to be the length of sigma. And then I have the integral of the kernel. And then one can check that the integral over the kernel can be computed explicitly, and this is equal to 1 over 2 pi. And this is a general thing, because if you solve this problem with u equal to 1, your solution will be u equal to 1, because that's an s-harmonic function with exterior datum u equal to 1. So here you would have 1 equal to the integral. Here you would have 1. And so this one here is not there anymore. And so you would have the integral 1 to plus infinity of the measure of the boundary of B1. And then you are integrating basically in the rho, which means that 1 is equal to the measure of the boundary of B1 multiplying the integral of Ex rho in the rho. So this integral is equal to 1 divided by the measure of B1. So this is the computation that is hidden here, that this object is equal to 1 divided by the measure of the boundary of B1, which is 2 pi in dimension 2. So again, I can write explicitly the solution in a kind of a simple way and using these geometric considerations. Okay, and again, I'm not proving the fractional Schwarz theorem, but the idea is the same. It's the same as the classical case. So you use the fractional Malmheden theorem with dimension 2, and you check the algebra. So you basically check that, more or less doing the same computation done in the classical case. If you start from the expression that we have in the Schwarz theorem, you do a bit of manipulation, then you end up with the expression that you have in the fractional Malmheden theorem that you have already proved. So it's really a bit of manipulations, a bit of algebra, and the clever use of the spherical change of variable. So that's essentially the same. Okay, but here a couple of byproduct of Malmheden and Schwarz theorem in the fractional setting that are kind of interesting, and we will see they help us improve in a couple of things, especially Harnack inequality with optimal constant. That is kind of an important thing. So as a byproduct of the Malmheden theorem, the fractional Malmheden theorem, we can see that an s-harmonic function is the superposition of classical harmonic function. And this is the theorem. So for each rho, I consider U of f rho to be the unique solution to the classical Dirichlet problem in the ball B1. So it is classical. Laplacian of U f rho equal to 0, U f rho equal to f rho on the boundary of B1. Then the solution of the fractional Dirichlet problem in the ball, so in the ball B1, so fractional Laplacian equal to 0 with U equal to f in n minus B1, can be written as a superposition of harmonic functions. This superposition is weighted by the same kernel that we had before. And the reason is because if we go back, for instance, to let's see, to Malmheden theorem, you see, so if I just look at this integral over B1 of this interpolation, this was exactly, so just this bit, without taking the kernel outside. This object here was the Malmheden theorem in the classical case. So this object here, without the E, should be the classical solution of a problem with the Laplacian, not with the fractional Laplacian. So you can write U as the superposition of a function coming from here, which is now harmonic in the ball, multiplied, weighted by the same kernel. So it is basically straightforward. Once you have Malmheden theorem and the fractional Malmheden theorem, you have this result. So this is straightforward. This is essentially the proof. So U can be written as the sum constant, which is now the measure of the boundary of V1 times the integral, just now in the row, of harmonic functions. So it's a superposition of harmonic functions weighted by the same kernel. And this is a nice consequence because we can give a new proof of the fractional Harnack inequality. So the fractional Harnack inequality has been proved, for instance, in the, it's contained, for instance, in the thesis of Maurice Kasman. But here we can give a different proof, so using the classical one, and we can also obtain optimal constants and prove that in the limit when s goes to 1, we recover optimal constants in the classical Harnack inequality. So this is the theorem, and this is basically the last theorem of this short course. So if U is s-harmonic in B1, then for each ball, for each radius r in 0, 1, so for each ball BR, and for each point x in BR, so U of x is comparable with U at 0 with explicit constants, which are 1 over 1 minus r squared to the power s divided by 1 plus r to the power n, and 1 minus r squared to the power s divided by 1 minus r to the power n. So this is the fractional Harnack inequality. The constants are optimal, so you can't do better than this. And also, when s goes to 1, these constants converge to the optimal constants of the classical Harnack inequality in BR for harmonic functions in B1. Okay, so the last proof of this short course is the proof of this fractional Harnack inequality. So we will use the fact that an s-harmonic function now can be written as a superposition of harmonic functions, and we can apply Harnack, classical Harnack, to the harmonic functions. So applying the Harnack inequality for classical harmonic functions to the UF rho, we have that UF rho is bounded by the constant that we have in the classical Harnack inequality multiplied by the function evaluated at x over rho. And so from this, so if we use the fractional Malmheden theorem, so we obtain, so U of 0, we said is equal to this constant, and then the integral from 1 to plus infinity of U, the function U, multiplied by the kernel. The kernel can be written, so the kernel was evaluated at x over rho, so can be written, sorry. So U of 0, I'm using, where is it? So I'm using this superposition. So U of 0 is the integral of U f rho at 0, E0 rho. So this is omitted here, but this is the first step. And then I'm using the fact that U of f rho 0 is bounded by this object. So I have the kernel at 0, and then here, this comes from UF0 bounded by this object. So this object is here. So I'm using the superposition, the fact that I can write an s-harmonic function as superposition of a harmonic function in the first line, and the classical Harnack inequality. And then it's a matter of manipulating a bit this object, because here I want to isolate the kernel at x rho. So I will multiply and divide by objects that allow me to isolate the kernel. Okay, and then I will put things together. So I have rho squared, rho n minus 2, which go into rho to the power n. 1 minus x squared is here. rho minus x gets simplified with rho minus x here, and then you are left with the rho plus x, which goes together with this one. So this goes to the power n. And then if I call g rho t this function, so basically this one here, and I call t the norm of x, this is nothing but g of rho t. And now I want to isolate this g of rho t because g of rho t has nice monotonicity property, so it's decreasing in rho and increasing in t. If you see it, it's decreasing in rho and increasing in t. You can check this one, can check it. And so at the end of the day, sorry, the supremum of g rho t is where, because it's decreasing in rho, is where rho is equal to 1, and it's increasing in t is where t is equal to r. So this is nothing but g of r1, sorry, 1r. Okay, and then if I use this information, I have the t of 0. So now g of rho t is below the supremum. So this is what is here. So this is below the supremum of g, which is this object here. And then I have finally the integral of e of the kernel at x u of f rho x over rho, and then I use again the superposition theorem, and I can say that finally this is together with the constant, this is equal to u of x. So this establishes one side of the fractional Harnack inequality. U of 0 is below some constant, depending on the ball, Br, multiplying by u of x. And the other side, well, I have to use the other side of the classical Harnack inequality for harmonic function. So now u of f rho is above, okay, multiplied by some constant that I'm putting here now, is above u f rho of x over rho. And so now u of 0 is again equal by the superposition theorem to the kernel at 0, which is here, and the constant is outside, times u of f rho is 0. And then I use the Harnack inequality above. So u of f rho is bigger than u of f rho evaluated at x over rho, multiplied by this constant. And then, of course, I will simplify a bit. I will do some algebra to simplify a bit this expression, and I will end up with this. And then the other thing that I want to do, I want to isolate e of x rho, because at the end of the day, I want u of x somewhere. I already have the function here, but I want the kernel. So I have the kernel here, and then of course I will have to multiply and divide by something, and I will end up with an object of this type. And now this will be my function g, that I will call g1, just not to get confused with the first one. So g1 of rho t, you see if t is the norm of x, g1 of rho t is rho minus t to the power n, divided by rho to the power n, 1 minus t squared to the power s. And then u of 0 is bigger than something of this type. Now I want to put, in place of g1, I want to put my constant, the constant that I want at the end of the day, because if I do that, then whatever remains is going to be my u of x, and I'm done. So this is a bit worse than the previous function, because I have to play first in rho. So this is not clearly increasing in one variable and decreasing in the other. You have to do it in 2 steps. So first you have to observe that fixing t, g1 is increasing in rho. So g1 of rho t is bigger than g1 of 1t, which is this one here. So we draw equal to 1. And then, okay, I can simplify. If I write 1 minus t squared as 1 minus t times 1 plus t, I can simplify the 1 minus t. So I have 1 minus t to the power n minus s, and then I have 1 plus t to the power s here. And now I call this g2. Okay, so this thing here will be bigger for any t of g2 of t. And now g2 of t is decreasing. Okay, so g2 of t is decreasing. So g2 of t will be bigger than g2 of R. So now I can say that this is going to be bigger than G2 of R. Looking at this, this is not decreasing in T as it is. You have to, for some reason, you have to pass to, you have first to do, you have first to use the G1 is increasing in rho, fixing T. So now this is decreasing, and so I can say that G2 of R is equal to this object, which I can write again the way I like. Okay, but nice. Now G1 of rho T is bigger than the constant that I wanted. And so I'm done, because this is the constant that I wanted. This is U of X with the constant. And so this is the other side of the fractional Harnack inequality. Okay, and then really the last slide and the last thing that you want to check is that the constants are optimal. I'm not sure this has been written somewhere explicitly, like with an explicit example. Okay, so I want an explicit example for which the ratio between the value of the function at 2 points is exactly equal to the two constants, so one of the two constants. So I'll fix an epsilon. So to construct these functions, I'll fix an epsilon, and then I will define U of epsilon to be an integral over a ball, B of radius epsilon, centered at epsilon plus 1 in some direction E, so in some unit vector E, of this object here. So now this is s-harmonic in B1, because I think this is nothing but, so this solves s-harmonic in B1 with the datum outside. I think it's the characteristic function of this ball multiplied by whatever was here in the Poisson kernel. So it's something like 1 over y squared minus 1 to the power s, something like this. And then essentially, this is nothing but the integral outside B1 of f multiplied by the Poisson kernel for a given f, which is the one that I just said. So this is s-harmonic in B1, that's the bottom line. So it's a good function that I could use, that I can use in the fraction. So it should all, the fractional Harnack inequality should hold for this function, right? Okay, so now let's write what U epsilon at 0 is. U epsilon at 0, okay, is x is equal to 0 here. So x is equal to 0. So this is the integral over the ball of just dy divided by y to the power n. And then if I pick x to be minus re, then U epsilon of minus re is again this integral. And here I have 1 minus r squared, because the modulus of the norm of x is r, and then y plus re to the power n. And so if I send epsilon to 0, so you see, if I send epsilon to 0, essentially this becomes, okay, so here I'm sending the radius of the ball to 0. So I think this should go to 1. And the denominator should go to 1 minus r squared, which is here below. And then here it should go, I think, to minus, I think it should go to e here. So this, so y should go to e. So this should give me, so you have to use basically Lebesgue differentiation theorem to do this, to actually do this limits precisely. But the idea is that epsilon is going to 0, so y is essentially going to e. And so here I have the norm of e, which is 1, and then 1 plus r to the power n, which is this one here. And this is exactly the one of the two optimal constants. And similarly, I think if you take x to be re, you would get the other, the constant on the other side. So this proves that you can't do better than this. These are the optimal constants in the Harnack inequality. Yeah, so I think with this, I will conclude this course. And I mean, I hope you enjoyed it. I I have learned many things while studying, especially the Malmheden Theorem was a new thing to me. So I was pretty happy to talk about this. It's the first time that I present this theorem. So I've also learned things while preparing the slides and preparing the course. So I hope you enjoyed it, and I really want to thank Juliana and all the organizers for inviting me. It's been really a great pleasure and a big honor for me to, being part of this very nice school. And hopefully, I mean, it's a bit sad because I'm speaking essentially to my computer. So hopefully next time it's going to be in person. We can come to Brazil and talk in person. So thank you very much. And yeah, I'll stop here.